Okay, let's move on to the seminar today. Our speaker is Phillip Isola, who did the PhD here at CCL with Ted Adelson. He then moved to do a postdoc with Alyosha Efros at UC Berkeley and a visiting researcher at OpenAI. I'm particularly excited to hear today Phillip speak about because his talk fits very nicely with a discussion that we've been having here for maybe 1 year since Richard Sutton made his famous blog post about having no structure at all. And so we've all had the discussion on how much structure do you want to bake in our agents. Let's hear Phillip speak today. Thanks.
Okay, thanks for the intro. Yeah, I wasn't going to mention the Sutton post because it caused some controversy, but that's quite relevant here. He had a kind of extreme position of, bake in nothing, and I'm going to argue that we want to head in that direction. I don't know how close we'll get to really, bake in absolutely nothing. Okay, but this is an old set of ideas, emergent intelligence. I'm going to talk about. I thought I should talk about EI because we're in that seminar, so I'll talk about emergent intelligence. Okay, I hope I didn't get the wrong EI, but that's okay. So it goes way back. The background is some cellular automata from Conway's Game of Life, and I'm not going to talk about that at all, but that's just to motivate this idea of getting complexity out of simple rules. Okay. So the way that we've been thinking about this, I've been thinking about this, is we want to create algorithms that produce more structure and intelligence than you put into them. Okay, so we can think of it kind of like baking. If I'm going to make some chocolate chip cookies, I want to start with really simple ingredients, and my measure of success is how much better is the thing I got out than what I put into it. Okay, so we want to maximize kind of the return on investment of our AI algorithms. I want to get more out than I put in. So what would the recipe for intelligence look like? There's a lot of ideas out there. One of the kind of classical ways that this was done was that you just coded the AI. You didn't do learning, you didn't do optimization. You just wrote down a bunch of rules, and hopefully the rules would combine to create something that was intelligent. But there wasn't that much emergence. You kind of try to write the program by hand. And over time, people added different kinds of ingredients, different kinds of structures from which an intelligent system should emerge. In computer vision, we focused a lot on geometry and optics and physics. But these days, what's most popular is to let the intelligence emerge from data. So we code our algorithms with data and labels. In reinforcement learning, there's another paradigm that has come along, which is don't use data, but use environments. So you create environments and tasks, and then you let a reinforcement learning agent figure out how to solve things in order to maximize its rewards. Okay, and this is kind of going down the spectrum of baking, I think, less and less in. So there's less and less kind of hand coding involved in using data compared to writing down a bunch of rules. Okay. And there's a lot of other things you might bake in too, various inductive biases, architectures, neural net architectures, regularizers, the optimization choices. But what we want is we want AI to come out, and we want to figure out what is kind of the minimal recipe that you can put in. Okay. Or what's the easiest recipe? Other people might say, no, data is super expensive. It's easier to write a program to solve certain problems, and that's totally legitimate too. Okay. So I'm going to talk about 3 snippets of research that I've done, and it'll touch on research in the field in general, where we put in some information, and we got something that was somewhat surprising out, where I think that we got more out than we put in. And I'm going to use these snippets to exemplify 3 principles. Okay, so the first one that I'll talk about is the idea of finding the right inductive bias. If I have a lot of data, and I want to extract intelligence from it, well, I might have to design a good inductive bias, like the idea of compositionality or modularity, or the idea of convolution, that the world is spatially invariant, that objects at one location look the same at the object translated a little bit to another location. So I'm going to talk about one piece of work that we did where we saw something emerge from a simple inductive bias. Okay. So the topic is going to be representation learning. And a couple years ago, we were working on a related topic, which was, well, it didn't seem related, but it turned out it was. It was colorization, okay? So the goal was to take a black and white photo like this one here and to predict the color values in the photo, okay? So the input is the L channel in the LAB color space, and the output was the A and B color channels, okay? So visualization of what A, B color channels look like is up there if you're not familiar with it. And you could put these things together and get a beautiful colorization of the fish. So we ran this algorithm. We trained a deep neural net to solve this problem, and it could make fairly accurate colors. It was able to color the fish yellow and the background kind of bluish and greenish, which was correct. And so we ran it on a bunch of images, and one thing that we noticed is if you run it on these dogs here, it does a pretty good job, right? But do you notice anything a little bit weird about this image? It got the background is green, the grass is green, the fur is just regular whitish fur. But there's something else going on, right? There's a little blotch of pink underneath the dog's mouth. So why? Anyone have an idea why? I think it's pretty clear, right? What is it? It's the tongue, okay? And we looked at our data, and it turned out that in the training data, every single dog had its tongue out. Okay, this is ImageNet. ImageNet's mostly dogs. It turns out to be mostly dogs with their tongue out. So the network has no evidence of there being a tongue in this photo, right? Because there is not a tongue. It's just fur under the chin. The reason why it hallucinated a tongue, why it hallucinated the pink there, is because it must be because it has seen dog faces and it's recognized the idea of a dog face, and it knows it has this kind of prior that if I see two eyes and a nose, I probably should have a tongue underneath. Okay, so it seems like this network that's only trained to do colorization has learned something about the semantics and the geometry of dogs. So that led us to probe things a little bit more deeply. And we used this trick that a lot of people have been using over the last few years, and that is to act like a neuroscientist. And you take your network that's been trained to do some task, in this case to colorize the image, and you stick a probe inside it, and you measure each neuron's response to a set of stimuli. And you can find some neurons that fire, have high activation whenever they see a fish, and other neurons that have a high activation whenever they see a stripe pattern. You can learn about what these neurons are detecting, what they're actually doing. And the interesting thing with the colorization project is that if you do that, you find neurons that are highly, somewhat selective for faces, and somewhat selective for even dog faces and other kind of semantic categories, flowers. So a lot of you may have seen this before. People like David here have shown that you can dissect neural networks and find detectors for all kinds of semantic categories. But what was really exciting and surprising at the time to me is that these detectors emerged without any labels in the training process. Okay, so it's not surprising that if I train a neural network to recognize dogs, it'll have some neurons that recognize dogs. What is a bit surprising, what is a bit emergent, is that a dog detector comes about when the task was only to predict color values. Okay. And we can quantify that in various ways. So one of the ways that we use to quantify this is we look at the neural representation of an image, and we ask, in that vector space, which we call Z, does the representation of dogs and cats get linearly separated from the representation of other semantic classes? So we ask, is that code for the image, is that vector code informative about object class in a linear sense? And you can do that by training a linear regression on top of that layer and seeing how well it classifies between semantic categories, like the ImageNet categories. Okay, and when you do that, what you see is that if you train the network to predict colors, which we can think of as some half of the data from grayscale pixels, that's another half of the data, as you look at the representation evolve through the layers of the neural network, you see that you get better and better linear separation between the different object classes, okay? So we see that we kind of get this emergent representation of semantics in the layers of a neural network that was trained without any semantic information, at least no explicit semantic information. Yeah, question?
Why is thinking about a linear classifier sort of
I think it's not the ideal evaluation metric. What you really might want is to say, can a representation support few-shot learning? Okay, so if I have a couple labeled examples, how quickly can I tune this representation to classify those labeled examples? And a kind of proxy for how well does it do at few-shot learning is how well does it do as a linear classifier, because linear classifiers can be trained with relatively little data. But this was just kind of a protocol that we kind of arrived on and standardized, and it might not have been the best choice. I saw there was a paper that came out a couple days ago, and there were some tweets like, why are they doing linear readoff? That was such a bad idea. You know, who made us do this? And I think it came from neuroscientists, because that's where at least we got it for this paper. They like to look at representations in the brain and ask how linearly separable are different semantic classes. Okay, so we can blame the neuroscientist. Okay, so colorization is not the only task that results in emergent semantic representations. In fact, whatever predictive task you do on the data seems to work. So you can get a representation that can linearly classify semantics by colorizing photos. Suppose we try to predict sound from an image, and you can get kind of the same thing. In this case, the classification accuracy was slightly lower, but in general, these so-called self-supervised objectives work quite well. So the idea is that you take one sensory modality and you predict another sensory modality from it, where you take one part of your data and you predict another part of your data from it. This idea is super popular right now. It exists in NLP all over the place, where you predict like the next word or a missing word. It exists in all kinds of machine learning right now. Okay, so predicting one part of the data from another part of the data without labels results in really nice representations. So the next question is, why did these representations emerge? Why did semantics come out of doing something like predicting the cone response from the rod response, or the ear's response from the eye's response? And this is something that we've been thinking a lot about. And for me, I think the best analogy is this allegory of the cave. Okay, so this is a story that you might be familiar with, where Plato wrote that humans are kind of like dwellers in a cave, where outside there's the actual reality, the Platonic reality. And in this cave, you have a bunch of people that are chained up, and they can only look at the shadows cast on the wall from the outside reality. Okay, and their whole notion of what reality is just the projections of the real, Platonic outside. Okay, and I think that this is a great allegory because it's actually true. It's actually how perception works. All of the senses that we have are just projections of whatever exists in physics. They're not complete, right? So we have something, a 3D model, an animal out there, and we don't see the exact 3D. We don't see the true state, whatever that might be. We just see some projection of it, some 2D image. And we get other types of projections too, and they're noisy and they're incomplete. We also get the sound. And the kind of key idea, the key inductive bias that I'm going to get at is all of these projections, all of these sensory measurements of the underlying reality are generated by the same thing. They're all generated actually by that cow. Okay? So if we can find a representation of an image that is aligned with the representation of a sound, then it must kind of arrive on the common factor, which is the actual cow. So in the colorization approach, what you do, or the sound prediction approach, is you take the image and you try to predict the sound, but the only intervening variable that can explain the relationship between those two things is hopefully the actual semantic thing, the actual cow. And that seems to happen. Okay, so let's look at it one more way. We have our Platonic state space, the actual cow, and it generates a lot of observations. And the observations are all entangled and noisy and incomplete. Okay, so it generates an image, and it generates a waveform, and it might generate a bunch of images, because as I move my camera around the cow doesn't change, but I get a bunch of different observations of the cow. So this cow generates all of these observations, right? And the idea of multi-view representation learning is that Okay, this is the colorization thing, or the sound prediction thing, but the idea of multiview representation learning is you can kind of flip that around, and we can try to learn a representation where every single sensory view of that cow are mapped to the same point. We want to be invariant to the view, and we might have a touch sensor, and then we want the touch sensor to map to the same point, okay? So the key inductive bias that I think makes these things work is that it's the idea that the way you measure the world does not change it. There exist some physical things out there. However you measure them, the semantics, the physics are unchanged. Okay, and this is, I think, really intuitive. If I move my camera around a cow, it still is that same cow. If I have a cow named Betsy, why is it called Betsy? It's called Betsy because, if I see a photo and I label it as Betsy, and I hear some sounds and I label them as Betsy, that's just a cluster of observations. It's a cluster of many different observations, sensory observations, that all map to this same point. Okay? I think this is something that we kind of take for granted. Kind of an exception that proves the point is quantum mechanics, right? In quantum mechanics, people were super surprised when it turned out that if you measure a wave function, it collapses, right? Measurement changes reality. That was super surprising. Normally, measurement doesn't change reality, and that's the inductive bias that we're using here. Okay, so a lot of people have used this basic principle. One of the latest ones that we put out there, we called contrastive multiview coding. In this paper, the kind of technical details are in this diagram here, but it's the same idea that I've already motivated. We can have two views of a scene. In this case, the two views are the L channel and the AB channel, just like we were doing with colorization. And we learn a mapping, F, that will map the color channel to the same location as the corresponding black and white channel in latent space, okay? At the same time, we want to make sure the representation is not degenerate. If I took the colors and the black and white for all images and mapped them to 0, I would have perfect alignment between all of my views of the data, but I would have a meaningless representation. So at the same time, we take some negative samples, so colors that come from a different image, and we encourage those colors to project to a faraway point in the latent representation compared to the colors from the actual congruent sample. Okay. So that's really all that there is to it. There's a lot of ways of learning representations like this. You can use what are called contrastive losses, like we use here. You can use something that was called a triplet loss, where you just try to bring together positive pairs and move apart negative pairs. They all do essentially the same thing. And these methods are getting exciting right now because they're learning representations that aren't at 30% linear classification of ImageNet categories, but at 76% as of a couple days ago. And 76% is now on par with fully supervised methods. Okay. One more thing that you can do when you have this perspective is you can say, well, if all the different ways of looking at the world should agree upon the underlying semantics, well, why don't we just add more and more ways of looking, more and more views? And we'll try to make sure that the black and white channel and the color channels and the depth map and the semantic segmentation map all project to the same point when they are sensory measurements of the same scene. And when they're sensory measurements of different scenes, then they should project to different points. And if you do this, as you add more and more views, your representation quality gets better and better in terms of how well it captures the underlying semantics, how well it can linearly separate some semantic categories. Okay, people have recently started doing something that's kind of analogous to this, which is they call it data augmentation, where your views are synthetic views, and they come about by just randomly perturbing an image. So it's like you randomly remove some pixels. That's like a different sensor. So you have a bunch of noisy sensors, and you find what they all agree upon. Yeah.
So, like for this room example, if I were to like take a video of this room,
Yeah.
I feel like you need to be really careful about what's a positive and negative pair, right? Like, are two
You do.
different views in the same room? Is that a negative pair or a positive pair? And like, there's quite a bit of work there.
Yeah, so how you define the negatives and positives is what kind of defines what semantics you'll pick out or what property of the world you'll pick out. I think in the most obvious setting, if I want to have a system that can recognize object instances, then it makes a lot of sense. I should move my camera around that instance and say that all those photos should be represented identically. But if I want something that will generalize across instances, so I want to say cars, yeah, so not have a representation where this car, no matter how I look at it, is the same car, but all cars map to the same point. This explanation doesn't tell you exactly how to do that. It turns out that learning representations that are invariant to how you look at an instance results in a representation that also is good at classifying categories. But that's a bit of magic. Maybe that's another kind of emergence that we don't fully understand. Okay, any more questions on this part? Yeah.
That first network, was it learning to colorize only the types that you had in your data set, or was it really learning to colorize things outside of the data set?
So that's a really good question, and yeah, more the former. You might generalize a little bit outside the data set, but one point is that the data set it's trained on is ImageNet, and there's 1,000 categories, and baked into the data, there might be the category information. Now you can train on ImageNet and then see how well you can generalize to a completely different data set, and it does okay but worse. Yep.
It makes sense to me that different physical views of the same physical object, different modality views of the same physical object might map to the same place because it's all this thing to
Right.
work out. But has anybody who's ever encountered the kind of remarkable screeches that a cat can make when they're fighting and has been shocked by it, the mapping across those modalities is not so obvious to me, and how one would get that, other than by, oh, here's an example of the kind of sound this thing can make,
Yeah.
even though you would never have imagined it.
Yeah, so I think that's critical is that you have to have seen that co-occurrence of the cat shriek and the appearance of the cat in order to, that's what provides the supervision in the first place. So I wasn't completely clear on this, but the supervision is because we have paired sensory measurements. We have the cone response and the rod response, and we know that they co-occurred, and we call that a positive. In the sound and vision case, it'd be the same.
And we're supplying the semantics.
We are supplying the semantics in how we define the views. Yeah.
Sorry.
We are supplying the semantics not by having a human label every image, but in a somewhat weaker way by just defining what the two sensory views are.
But
That's where it's coming from. So it's not, I think the goal is not to have things emerge from nothing, but to have them emerge from as little as possible. And so we're pushing in that direction. Yeah. Right. Maybe there's no free lunch, or like there's no way to do it from absolutely nothing. Yeah. And I think that's actually really important because some people like Richard Sutton might be seeming to suggest that there's some magic that can happen, and there's not really. Okay. Okay, so the story here, this is just one inductive bias that I think leads to something emergent, and it was somewhat surprising to us that it worked as well as it did. And the way I'm summarizing it is that the way you measure the world does not change it. You enforce that bias through your training objective, and then you train a CNN, that's another type of inductive bias, on a bunch of raw sensory data, which has to be collected in some nice way. And you get this notion of semantics falling out. Okay, so it's kind of like semantics have emerged from physics, right? From properties of the universe, not from arbitrary like human cultural definitions. There's a reason why all cultures have a word for cat and dog and cow and so forth. They don't? Okay. Well, yeah. Not getting into the NLP details, but
Sorry, not to.
yeah. Go ahead.
It's sort of an important point, right? The way you're evaluating all of these things is by the measuring how well they predict, like basically object identity class labels or scene identity class
Yeah.
labels or whatever. Is that the only downstream
That's, well,
test that you're evaluating on?
there's more in general that people look at. Some of them are things like even geometry prediction or depth prediction.
Yeah.
But I would say for the kind of semantics, it's usually object categories. And if you wanted to predict something that are more kind of attributes or adjectives, I imagine there'd be less agreement between different cultures, but I don't know.
Yeah. Well, I guess just more generally than that, like are we predicting semantics in general, or are we predicting
No, this is,
Are we learning something about semantics in general?
yeah.
Or are we learning something about like human objecting conventions?
I think the conservative story is the latter. Yeah, the conservative version is the latter. Or you could say things that co-occur get similar names. Yeah. So how far that extends to all of semantics is an open question. Yeah. Okay. So I'm just doing three little snippets. So I'm going to go on to the next one. And the next one, I got the name from this paper, this classic paper called More is Different. It argues that in certain complex systems, when you have a lot of things, they behave in an emergent way that is unlike and unpredictable from the constituent elements. Okay? So in biology, a bunch of cells make an organism, even though the organism doesn't look at all like the cells, and it's hard to predict what an organism would do if you just had a description of the cells. Okay, so I think this happens also in machine learning and in AI, and what often happens is once you get enough data that you train your model on, interesting things start to happen. Interesting things start to emerge that you might not have expected or seen when you tried the model on smaller data. If you tried the model on MNIST, you might not be that excited. You try it on ImageNet, and suddenly you get some interesting properties. And the interesting property that I'm going to look at here is what happens when you train a generative model at very large scale on static images. The model is a convolutional neural network. And what seems to happen is you get these physically plausible continuous dimensions. And I'll show you what that looks like. Okay, so we're going to be looking at now generative modeling. And these are samples from one of the latest, greatest generative models. This is samples from Big GAN. And I think that this is interesting, but probably the least interesting aspect of generative modeling is just making random beautiful photos. Okay? It's really cool. You can make photorealistic photos, but we already knew how to do that. We could just go on to Google and randomly pick a photo. Okay. So what we would really want in a good generative model, and what I think my dream of what a model should be, is something that's more like a graphics engine, a video game, where you can navigate the model, you can steer around in that model, you can control it, you can make predictions with it, and so forth. It's really like a mental model of the world. It's not just a bunch of samples. Okay, so how close are we to making models, generative models, that act like a 3D graphics engine? Okay, so one more way to motivate this is, well, data samples aren't that interesting on their own. We already train our models on a bunch of data samples. But what's interesting is when you fit a model to it, it kind of fits a continuum to these discrete samples. And the continuum is what's interesting. And here's what I mean by you get kind of physically plausible underlying dimensions, where now we have something more than the data itself. We actually can look at the faces rotating as we move through this latent space. We can interpolate between them. We can even extrapolate a little bit. So let me show you how this works and how we've started investigating it in some of our recent work. So we're going to be looking at deep generative models that have the form of latent variable models. So you start with some latent random variables. Usually they're Gaussian distributed variables that we call Z. And we put them through a neural network. And the neural network at the end has reshaped that noise, that random noise, into a photo. Okay, so you can think of this as a mapping from a simple distribution, the Gaussian, to a complex data distribution, this blue blob. Okay, and if we sample a different random Gaussian vector, we'll get a different random image at a different location on the image manifold. Okay, so we go from this latent space to the data space. And it's the opposite of what I was talking about in the first section. So this is the opposite of representation learning, essentially. We're not going from data to simple latent space. We're going from latent space to complex data space. But the really, really cool thing that comes out is that if you look at a point in latent space, and you look at another point, and you draw a line between them, well, as I walk in a line in latent space, I map out some kind of trajectory in data space. And it turns out that I map out a trajectory that looks meaningful, okay? So here we have a latent vector that corresponds to a bird and another one that corresponds to a fly. And when I linearly interpolate between those two latent vectors, I get these morphs that turn the bird into the fly. So it looks like something meaningful is going on here. Of course, that can't exist in reality, but it seems to have captured something more than like linear blending. So we wanted to investigate to what degree there are simple latent walks that you can take that correspond to meaningful physical transformations. Yeah.
So is there any meaning to the probability density of each of the points during the interpolation? Because say you're interpolating from a bird to a fly, if it's based on real life, the images in between should actually have low probabilities of occurring. But if it's going through a region of the Gaussian which actually peaks the probability, is it really learning the underlying distribution of these images?
So oftentimes we'll constrain the walk to be on kind of equal probability contours. So like the surface of the hypersphere is one way to do it. But in general, as you walk through the Gaussian, through the center of it, you are navigating different probability densities. Now these models also are not always going to be likelihood models. This is a GAN. So the relationship between the probability in Z space and the probability in data space is not something that you can exactly state. So yeah, that's a good question, but I think for now, think of it as we're kind of walking along equal probability contours. Yeah.
Are there also paths that when you look at them that don't make any sense?
There are some, yeah.
In the way that you
Yeah, but not very many. Well, okay, glass half full, glass half empty. I would say there's kind of seams in the space. Like I think Jonas, if he's here, has been working on that problem. So there are these nice smooth paths, and then there's a seam, and then another nice smooth path. So you get these weird abrupt transitions, and that might be because you're trying to map this complex topology onto a sphere, and you have to have cuts and seams.
I was less concerned about continuity than an eye of the beholder phenomenon. A path corresponds to something meaningful. Well,
yeah.
if you pick out the right path, it does.
Right.
And if there are unmeaningful paths, then the semantics are all eye of the beholder phenomenon.
Yeah, so I would say that most random paths you take will look, to my eye, meaningful. Now, what we're going to be doing is optimizing the path to be as meaningful as we can make it. But it's still, we'll only be looking at linear paths, and so that constrains us from kind of cheating too much. Okay. Okay, so this, we started investigating, what is, the geometry of latent space and what properties does it have. And one of the papers we've done is this one with Ali and Lucy on this durability of generative adversarial networks. And here what we wanted to do is just say, look at, in the latent space of these models, are there simple camera transformations? Do they act kind of like a video game in which you have the most basic thing you have is you can move the camera around, you can turn the lights on and off. Do they even capture those kinds of transformations? Okay. So how close is the GAN to this classic graphics engine? Just in terms of camera movements and color transformations. Okay, so here's what we did. We learned a vector in latent space that's a linear direction that corresponds to a path in image space that matches some kind of target operation. Okay, so the target operation that I'm showing here is shifting the image up vertically. Okay, it's panning the camera up. So the loss function for training, for optimizing and learning this W is to take an image, G of Z, made by the network, edit it, shift it up, and try to come up with a vector W such that G of Z plus W generates the shifted up image. Okay, so here's the objective. We want to say G of Z plus W should be similar to some edit operation on G of Z. So if we shift the image up by amount alpha, that should correspond to walking a distance alpha in the W direction in latent space. And this is a simple optimization procedure. W is a 140-dimensional vector because latent space is relatively low dimensional, and it's just a vector. Okay, we're just going to walk in a line. Okay. So this idea kind of goes back to this notion of word Tyvek, where you get emergent representations in language models that where directions are semantically meaningful. Okay? So a famous one was that in this vector representation of words, the direction between king and queen is the same as the direction between man and woman. So the direction seems to be kind of a gender direction. And people saw that with present tense and past tense, walking to walked, and swimming to swam, and also capital to country, Spain to Madrid, and Italy to Rome. Okay, so the question is, do we also have vectors like this in image GANs? Do we have a zoom-in vector where I can walk in a direction and the image zooms in? Do we have a shift vector where I can walk in a direction and the camera pans left and right? Okay, so it turns out you do to some degree. So here's the zoom vector. It's a little bit shaky. We optimized to find the vector that's closest to zooming in on a photo. Okay, here's the shift vector. Okay, we can do a light vector, brighten the image. We can do a darken vector. So a little weird thing happened there. We didn't really capture the independent lightness factor. It's actually correlated with the volcano exploding, and so it models that. Okay. You can even say, what would happen if I walk in a circle rather than a line? And if you walk in a circle, you start to get these 3D transformations. Things that look like 3D transformations. And remember that this is a GAN that's trained only on ImageNet, only on 2D static images. And yet it's kind of self-organized to have simple paths in latent space correspond to what we'd think of as geometric transformations or camera transformations. Okay, so that's the kind of emergence that I'm interested in here. We wanted to quantify to what extent these transformations actually have been achieved. And one thing that we noticed is if you take this hot air balloon and you try to shift it up or down, it kind of works. But something weird happens at the edges. It gets stuck. You try to shift the hot air balloon out of the image, and it gets stuck. You can plot this. And we see we get this kind of sigmoidal curve, right? So as we try to move the hot air balloon up, eventually it stops changing. We saw the same thing with a bunch of different transformations. If you try to zoom in on this cat, there's a region where it works really well, and then once the cat fills the whole image, you just can't zoom in anymore. Okay? For rotation, the model really just can't rotate pizzas at all. So we were wondering why that is, and we thought it's probably related to bias in the data. Probably we've only ever seen cats at some scale, so there's no way for the model to know what they would look like if you zoomed in on them to be out of frame. Okay, so what I'm going to plot here is if we have a detector that can find where an object is located in an image, and then we try to shift the object's position, we're going to look at how much the detector's response shifts. Okay, so this is a histogram of the average position of objects in ImageNet. Okay, so usually they are kind of centered, and that's the bias that we're all familiar with, that most ImageNet photos are centered. And as we use our model to shift that distribution, it actually works somewhat well. It actually extrapolates out of distribution to a degree, but it can't extrapolate entirely out of distribution. So what happens is we shift the hot air balloon up, and then it kind of gets stuck at the edge. So we can only shift it about 50 pixels maybe, and then it gets kind of stuck. The same thing happens on the other side. So there's kind of a mixed story here. We can extrapolate outside the exact distribution on which we trained. We can shift the distribution. It's some notion of extrapolation, but it's not perfect, and there are limitations. You can't go entirely out of the support of the data that you trained on. Okay, so there's some kind of emergent generalization, but it's not, complete. We can even look at how the ability to achieve these transformations is related to the biases in the data set as follows. We can measure, I'm actually going to show this on the right over here. We can measure for each category what is the distribution of object sizes of that category. And what we see is that if there's a category like laptop that appears at many different sizes, then you can modify the size of a laptop more freely. And if there's a category like robin that only appears at one canonical size, then the model cannot zoom in and out on the robin as effectively. So there's a relationship between the spread of the data and how well the model is able to capture these transformations. Yeah, question? Yeah. Yeah. So the transformations, oh, yeah, the question was, this suggests that the transformations are not common across objects. The transformations are class specific, and that is true. And that's a problem because humans seem to kind of disentangle the camera transformations from the semantics, and these models don't perfectly disentangle that. So I think, yeah, that's one of the current problems with the models. Similar to the volcano exploding when you tried to turn off the lights. Okay. But also a good challenge problem. How can you get better disentanglement of these basic transformations? Yeah. Yeah, well, to me, the interesting thing here is that we trained it in a way that seems to be agnostic to humanity. Seems to be just, we're going to do a statistical model that tries to fit natural images. And it finds an organization of latent space that correlates with things that we have names for. Now, how you actually quantify that is a little unclear. To me, it's kind of, I know it when I see it, like you look at these interpolations and you're like, oh yeah, that looks more meaningful than linear blending or something that is more naive. But I don't have a precise definition of what meaning there is. But I think the interesting thing is that this kind of rationally motivated model that just tries to fit data in the world arrives at a similar organization as how I think humans organize the world. But we didn't do like psychophysical studies or anything like that. Yeah, that's a good idea. Let's see, in this case, we didn't have that inverse transformation. That would be interesting to look at. But we did try training nonlinear walks in latent space and see if those can better fit the zooming in and shifting. And it turned out that the linear is almost as good. So it seems like there's roughly linear directions that you can find that are effective. Okay, let me move on to the last section. Okay, so the last kind of recipe for emergence that I want to touch on is the idea of multi-agent interactions. So if you have a bunch of agents interacting, competing, collaborating in a rich environment, often that leads to some really interesting things. This is the closest to what people traditionally thought of as emergence, right? Okay, so it's the kind of thing that we have seen in the headlines in the last couple of years, like when you want to train an agent to play Go at superhuman ability, you can't just have it imitate humans because then it would, cap out maybe around human ability. So to get something that goes beyond humans, you have to set up this emergent kind of arms race. And the way they do it is with an adversarial game where one AI plays the other AI, or one AI even might play a copy of itself. And you get this arms race, and that creates competitive pressure for each player to get better and better and better. And eventually, maybe it plateaus at the actual optimum, at the Nash equilibrium of a perfect player. Okay, and we see this also in nature. This is something that's motivated people for a long time. You have all these arms races. The cheetah becomes faster at running, and the gazelle becomes equivalently faster, and then the gazelle learns how to jump, and then the cheetah gets stronger legs, so it can also jump, and you just get this kind of spiral, right? And that spiral is what we think led to all of the complexity of intelligence on Earth. That we had this spiral of evolution and survival of the fittest and agents competing for scarce resources. And eventually that led to the abilities that we have. So to me, this is a super interesting area. This is a very powerful kind of emergence, one that is baking in relatively little, but also very hard to harness as a result. But we've been looking at it in the last year or two. Okay, so I'm going to talk about one project where we looked at a moment. We were motivated by a moment in evolution that we think is quite important, moving from a single organism to a collective. This is the emergence of multicellular life. Okay, but we looked at this in a kind of toy setting. This is work that Deepak Pathak did, and Chris Liu. Deepak talked about it last year, you may have seen. But what we had is we had these primitive little cells, right? These little limbs. And they consist of a cylinder and a configurable motor that can attach to other agents. Okay? And what these do is they are allowed to move their motor around, wobble around, and they also have a special action, which is the ability to link up, kind of like a magnet. Okay, so two limbs can choose, by taking an action, to link together, or they can choose to unlink. And when they link together, they can create complex morphologies. They can create structures. Okay? Yeah. Oh, 5 minutes. Yeah. When they link together, they end up sharing rewards, and they are incentivized to do things like building towers and crawling across the landscape. Okay. So they sense the local configuration of other agents around them, as well as some environment properties. And the actions that they take are linking and unlinking and applying torques to each other through these motors. Okay, they can link up and form interesting towers like that. So we call them self-assembling morphologies. When they link together, they form a graph neural network. So they can control their behavior via a message passing algorithm. It's decentralized, but essentially every single node has a little policy network inside it, and it's getting information from the adjacent nodes and moving its motor around in response. And they have to learn to coordinate their behavior because they're sharing rewards to solve a task. Okay. So I'm going to show you some videos now, and I'm going to show you the one of the simple tasks that we do, which is trying to get the agents to form a tower. And the first thing that you might try is just to define a fixed morphology. I'm going to try to use reinforcement learning to train a snake of 5 segments long to stand up. So if you do that, this is what happens. I train one of these 1 segment long creatures, 2 segment long creatures. It still works. Everything is fine. But as you move to 3 segments, it starts to have trouble. And when you go beyond that, it really struggles. Okay, so this is trying to train kind of a fixed morphology. The agents are not allowed to link or unlink, and training is all this monolithic process. And it's hard because RL in high-dimensional action spaces is hard. Instead, if you train them where they start out as these independent agents, but they are greedy, and they eventually learn that if they link together, they can achieve higher reward because they can get higher, then this happens. Okay, so they start out as just a collection of agents, and they get this kind of curriculum where they gradually start linking up, and then pairs of agents might discover, oh, I can coordinate my behavior in just my pairwise behavior to form little subtowers. And over time, they kind of build up this modular structure and get larger and larger, and eventually they can solve the task. So we have all of these little modular creatures that end up self-organizing to create structures that we didn't really design, and we didn't know what they would look like. Okay, so this video will show a couple of the interesting behaviors that you get. One of the important points here is that these collectives are quite robust to perturbations. So you can train the collective to assemble a 6 long tower and then give it 10 limbs and it will, or 12 limbs, and it will assemble a 12 high tower, or it'll try to get there. It can also generalize to having fewer limbs. So we can you could have somebody that takes a limb out of this agent and it still will work. It will just click back together in a new configuration. So they're quite robust because they've experienced all types of combinations during training. This is in contrast to a monolithic morphology that's just fixed for all time, and if you chop off a leg, it will not know what to do. You can also train these things to run across a landscape. And again, we could have designed a humanoid to do this, but instead we get something more effective than a humanoid, which is this like slime mold creature that crawls across the landscape. Okay. You can give it more limbs or fewer limbs or put up different kinds of obstacles, and it works reasonably well. Okay, so it can also, it's never seen hurdles before, but it sort of figures out how to make its way across the hurdle landscape. This video is longer, so if you're interested in seeing the different creatures that emerge, feel free to check that out online. Okay, so I'm going to just wrap up in a second, but I also want to mention that this area of multi-agent is somewhat new to me and us, but we're really excited because we feel like it is a very powerful way to bake in little and get out a lot, get out some really surprising things. So one of my students, Joseph, is working on this big simulation of a massive number of agents, so a massively multiplayer agent environment, and just released a new kind of update to the platform and is interested in getting collaborators to play around with this platform. So the platform has up to thousands of agents or hundreds of agents, and they're all in this environment interacting, and we're interested in what kinds of emergent behaviors come about. So check that out if you're interested. And yeah, so 3 little snippets of kind of minimal ingredients that I think lead to interesting and surprising behavior that's not completely baked in. Those ingredients could be an inductive bias, just scaling things up to the point at which something different emerges, or creating these kinds of competitive and collaborative interactions that cause arms races or kind of emergent complexity. Okay, thank you. Question?
For the multi-agent part of the talk, is what causes that sort of generalization the fact that it is multi-agent with each agent having its own local objective, or is it more just because the computations are actually factorized in some way? Like, how much does the selfish objective actually help?
Yeah, so I think it's more to the factorization. So every single limb is actually sharing the same policy with every other limb. So kind of by construction, it has this modularity where I could add a limb and it'll just behave like all the other limbs. And they have to have learned how to work in all possible kind of configurations because it saw so many training scenarios with different configurations. So I think it's more about this factorization, that you factored the policy into a bunch of identical sub-policies that are all linked together. Yeah.
Did you notice if the greedy objective also has some benefits in some way?
Yeah, I think that's interesting. I don't know if we really looked into like how the incentives, like is it greedy or do you share rewards or not share rewards? We didn't really investigate those questions, but I think that's interesting. Yeah. That's right, yeah. Yeah. Yeah, so I think that's really interesting. This is me Joseph is actually playing with, like, how much do you share between different agents and how much don't you share? If you share a lot, you get these benefits of modularity. If every agent is different, then it can be kind of fragile because they might all specialize, and that if one of them is gone, then the whole economy breaks down and the whole thing falls over. But you might want to have some degree of specialization, so I think that's definitely worth looking at. In the self-assembling paper, I don't remember if we ever tried having different policies per limb. I don't think so, but yeah, it'd be interesting to try. Yeah.
What do you think is the right way to sort of imagine the first part of the talk? Sort of use those sort of learned representations, those mystery C's, to actually then do the downstream complexes and tasks. So is it really to enable
Yeah, I think the view I like the most is it's learning to learn quickly. It's, we want to come up with a representation that enables quick learning. And so few-shot learning is one, but it also could be sample-efficient reinforcement learning. That's also a form of few-shot learning. Maybe there's something beyond this, which is like zero-shot, where the representation allows you to do reasoning without any new data. You can just kind of, the representation acts like a model. In that case, it's not so much as just like a feature set, but it might be more like a model of the world that you can hallucinate futures and do planning. But for me, this kind of feature-like representation is best evaluated as how well does it allow you to quickly learn on top of that.
We'll take one last question.
This is sort of a follow-up to that.
Yeah.
So it seems like a fundamental limitation of representation learning in a statistical learning sense is that you're sort of always limited to the distribution that you have.
Right.
Whereas the mental models we learn, we can imagine things that are possible but not probable, and we can imagine things that aren't even possible in this world but could be possible in other possible worlds.
Yeah.
And we can distinguish those from things that aren't possible in any possible world, right? Like you can't have a square circle, right? I mean, again,
Yeah.
I love the analogy of Plato's cave, and these are classic ideas of philosophy.
Right.
So what do you think are ways that we could take representation learning, emergent learning, more in the direction that we can get beyond just models that learn what's probable to also learning what's possible, and even things that aren't possible in this world but might be possible in other worlds that we might somehow try to make?
Yeah, that's a good question. I think, one would be these right inductive biases. I don't know that we have them, but something like modularity or compositionality, where you have defined some semantics on what is possible, so that it's not just, like that you're always allowed to recompose these two modules in any fashion. So you don't have to actually have seen every configuration to know that that probability is epsilon above 0, but you kind of bake that in. But yeah, in general, I think it's open. To me, it's like you want those minimal ingredients. You do want those good inductive biases, but you want things that can be baked in with minimal human effort. So maybe compositionality can be baked in with minimal human effort, but it might go a long way in obtaining the kind of performance that we want. So it's a lot baked in the sense that it does a lot, but it's very little in the sense that I could code it very simply. I could write it in math as just a couple, equations.